Hello and welcome to the Mathematics for Public Health Colloquium. I'd like to take this opportunity to acknowledge the traditional land that we are on in Fields. The Fields Institute operates for thousands of years, and it's been on the land that has been traditional of the Huron-Wendat, the Seneca and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we're grateful to have the opportunity to work on this land. I'm now going to hand over to our principal investigator and director, Kumar Murthy, who will introduce our speaker today.
Okay, thanks, Sarah, and welcome everybody to the weekly colloquium. I'm kind of delighted to introduce today's speaker, a person I've known for many years and who has, we were connected in a fundamental way with respect to the Fields Institute. Bill Shadwick was the first director of the Fields Institute, and so it's really good to have him back to describe his recent scientific work. He's going to be speaking about his work together with Anna Cascon, both of whom belong to now Omega Analysis. And the title of their talk is Predicting the Course of COVID-19. Bill. And
thanks.
Anna.
Yeah, I'm going to. So I should correct one slip. I was first deputy director. Jerry Marsden was our director. It was my invention. Anyway, thanks for the invitation, Kumar. This is something we've been working on for a very long time, actually, since May. I guess it was early May 2020 when Jean-Pierre Bourguignon pointed us to a seminar that was being done or had been recorded actually, and had been recorded by the State Research Foundation of Sao Paulo about, among other things, Gumford's functions, it turned out. And that kicked us off on a long project because, well, we'd never heard of Gumford's functions before. They're basically just a multiple of a Gumbel distribution. And the Gumbel distribution is something we knew a very great deal about. I promised some prospective viewers of this seminar that it would be probably the first and only one they'd hear on COVID-19 that mentioned the work of Élie Carton. But there's geometry at the heart of the Gumbel distribution, and that will show up in probably if I get to at the very end, in the spirit of Michael Attia, who liked to say that everyone should understand the first half hour of the talk and nobody should understand the last 10 minutes. So we'll try and reserve 10 minutes for the geometry. So the paper that's linked to the announcement was finished on Christmas Day. It was posted to the Med Archive the next day and then was finally approved by New Year's Eve, I think. So this is very new, and we're looking forward to having comments on ideas about the work. What we're doing is trying to create a method for navigating through the waves of COVID-19. Our focus on this is making accurate, by which we mean with errors less than 10%, short to medium term, 1 week to several weeks, forecasts of COVID-19 hospitalizations. And the reason is very simple. This is the fundamental requirement for dealing with an epidemic. Once we have accurate forecasts of demand, then reliable contingency planning is possible. And given the willingness of government to provide resources, the problem can be dealt with. So here's an indication of just how little we actually know, even now, about the transmission of the most familiar illness that's caused by a coronavirus, the common cold. This was published in 1973 in the Journal of Hygiene, Cambridge, now Journal of Hygiene, London, and describes how an outbreak of common cold occurred in Antarctica after 17 weeks of complete isolation. 17 weeks of isolation. So one might ask questions like, from whom should the person who got it first have socially distanced himself? And so on. So this is a very tough problem. The approach that we've taken doesn't require us to model infections or transmission or cases or the proportion of cases that will get into hospital. Modeling these things correctly, of course, would give the accurate predictions we're trying to get, and a lot more besides. But as you know, many of you, this is a very difficult problem. So our much simpler goal can be met by a much easier approach. What we're doing goes back to the basics of public health, back to the days of Farr's law and so on. We're counting cumulative hospital admissions, and we're using a simple phenomenological model, curve that approximates those running totals very well. So here are 3 examples. The data are the blue dots, or the dots if you can't resolve the color on your screen, and the curve is in red. So this is Danish cholera. There was a severe outbreak of cholera, and this is a few years before the John Snow pump handle incident in London. No one had a clue what caused cholera. So in a small town called Aalborg, Denmark, where the handwritten journal entries, records of the cases and deaths are still available. And thanks to the kindness of one of the librarians, we were able to get the data from them. The next example is cases of influenza recorded in the Portuguese National Health Service from the beginning of 2017 to the end of the flu season in the spring of 2018. Sorry, the beginning of the flu season, which was the beginning of December in 2017 through till May of 2018. And the final one is COVID-19 hospitalizations in Ontario last spring, the second run through last year's season from the 14th of March to the 14th of June. Now these fits are rather remarkable. The red curve is, of course, the Gumford's function. So this is given by this formula. Time is being measured in days. We start time at t equals 0. N is the unknown final number of events, deaths, hospitalizations, cases, so on. The constant A controls the rate at which the events grow, and B determines the fraction of events you see at time t equals 0, fraction of the final events. So given data, it's extremely simple to use nonlinear regression to get values of these parameters that give the best fit at any particular time. And as the epidemic unfolds, the parameters become progressively closer to their final values, the ones which you saw in those 3 curves. So this is a phenomenological model. It's not a new idea. Galileo had a good phenomenological model before Newton showed why it happened. Galileo showed that projectiles followed parabolic trajectories to a very good approximation. He did all sorts of clever things to eliminate friction. He couldn't eliminate air resistance, but he did eliminate a great deal of friction in his experiments. So a phenomenological model provides a mathematical formulation that can be useful for prediction, even though it doesn't explain what's going on. The Gumford's function is an example for epidemics, and it can be found in the epidemiological modeling literature, but not nearly as much as things with more parameters like the Richards function. So what we're doing is simply finding the parameters that make the best function fit Gumford's function for today, and then using that as our forecast into the future. So how well does this work? Well, that's a matter for empirical investigation. You would have to guess, given how well the fits are, how close the fits are at the end of the process, that somewhere along the way they start becoming predictive. So here's an example, updating weekly After all, there's not much use in a prediction that has to be updated every day, although that's better than nothing. So we do weekly updates, and you see the first one was high, but it still remained that the red dots are 10% plus or minus. So it remained within 10% for half of the weekly period, three days in a sample. And then very rapidly, these things converge to the final value. Skip over the influenza. And here's the same picture for hospitalizations in Ontario last spring. Again, the low ball fit from the beginning still stayed within 10% for a couple of weeks and wasn't out by 20% for a very long time. And then very rapidly after that, it converged to the final value. So that's the process. What about the errors? I mean, we're trying to make predictions, so we think the fair comparison is the gap between the observation and the prediction as a percentage of the prediction being what you would have prepared for if you believed this. So there they are in the Ontario case, and you see getting below 10% was not much of a problem. If there's time, I'll come back to this later. You see there's also, even when you get convergence to errors that are practically invisible, there's still significant errors in the in-sample way back at the beginning. It's because there are actually two different Gumford's functions involved in this process. Well, Galileo didn't just make predictions with his model. You might remember your high school physics class, you were asked to make inferences about the motion of a projectile using that model, typically before you knew enough calculus to know why it was true. And the very good fit between the cumulative event data and the Gumford's function allows us to draw inference as well. The fact that these things follow a Gumford's function as the epidemic progresses says that the Gumford's function dynamics are actually features of the time evolution of the epidemic. So what is the Gumford's function for the mathematicians? It's just a multiple of this Gumbel distribution, e to the minus, put in AT plus B as the parameterization. So N is the final total, which we don't know to begin with. That governs the scale of the epidemic, but the dynamics are completely driven by this Gumbel probability distribution. And you see, playing with this, that the function increases very rapidly, although never exponentially. It increases very rapidly, but its acceleration peaks early on, when only about 7% of the final events have occurred. Now, velocity is very asymmetric. It's a very rapid rise and a much slower decline. Here's the picture for hospitalizations in London. In the winter wave last from 2021. So this thing reaches its maximum at what we've called T2, which is minus B over A. And there, the proportion of the events that have occurred is 1 over E, approximately 0.37. Now this has immediate consequences for the idea of the herd immunity threshold. So we usually think of the first difference as being a good approximation to the first derivative. But in fact, we want to read that approximation in the other direction right now. It's the derivatives that's a very good approximation for the daily difference. The number of new cases we see each day looks like the derivative. In fact, you could see, you might be able to tell that there are two lines on that besides the noisy data, but the black and the red are almost identical. And that's because on the scale that we're working on, this is equivalent to a very fine grid on the on the natural interval that the real line where the standard Gumford's function lives. It's a grid with step size about a, which is typically well less than 0.05. So once you reach that peak velocity, the derivative is decreasing, so that number of daily events is also decreasing. Each day sees fewer people added than there were before. So this means that the reproduction number must be less than 1. Sorry, I see there's a typo. I always find them after the talk starts. That conclusion would hold if we were looking at cases, and cases were a good proxy for infections. Well, in fact, we know that in these examples, that's what we see. We see the peak and measurements much more difficult. The reproduction number starts showing up less than 1. So that's a consequence of the fact that we're following a Gumford's function. You can't follow it without having your peak at the same place that it does. So, and that's something that was a matter of a great deal of controversy in the spring of 2020, after the peak of the first wave of COVID-19 had gone through the northern hemisphere, at least. So we've been used the illustration of hospitalizations. This works equally well for cases and deaths. And as I said, if cases are a good proxy for infections, then once that velocity peaks, the reproduction number must be less than 1. And if you continue to follow the Gumford's function, the reproduction number will decline rapidly to 0. And that's what happened in the cholera example and many other outbreaks that we've looked at, and which are illustrated in the paper. Excuse me. That's not what we saw with the initial COVID-19 outbreak. What we saw there was that peak outbreaks past that peak velocity declined, and then the Gumford's growth switched. It switched to linear growth. Here are hospital admissions in London in April of 2020. We had an extremely good fit to the Gumford's function until about the 23rd of April. And from then on, we had almost exact linear growth. So this isn't just something where there's a persuasive line through a cloud of points. The R-squared is over 0.99 in these, and the errors between the graph and the line are very small. So this really is linear growth to an extremely high degree of accuracy. And what does linear growth mean? Well, it must mean that you have a reproduction number of 1. That's the only way you can have the same number of new events added in each time period. So again, we have to believe that cases are a good proxy for infections. Of course, there are a lot harder things to believe than that, which have to be believed all the time when you're trying to model COVID-19. But these periods have to be endemic. And we saw this transition to linearity again and again and again as we went through case after case after case, fitting Gumford's functions to the outbreak at the beginning, the first outbreak in 2020. Linear growth. And then we discovered by accident an example of a yearly cycle of transmissions between Gumford's function growth and linear growth. And that's in endemic influenza. So we found this, as I say, by accident. Gabriela Gomez, whose work I recommend to you, kindly gave us a link to Portuguese COVID data. And when I went to the link, totally uncharacteristically, I actually read the README document, which I think Gabriella could not have read because she didn't know this was there. In that document, I found a link to years of Portuguese daily influenza data, case data. We're hoping that we can find the same data, which this must, I think, be the result of a European Union initiative. So we're hoping that we can find similar data for other countries. And it would be very interesting to know if that data exists in Ontario or anywhere else in Canada. So this gave us a way of looking at the influenza cycle over several years in detail. So here's what it looked like. It continues to look like this with the annual bumps, even in 2020. It's just that the influenza was reduced to such an extent that you could not see the 2020 bump if I bothered to extend the x-axis through that year. You'd only see the previous 4. But this is a good example of why we like to look at cumulative data, because there are things you can observe easily in the cumulative that are very difficult to see here. What you do see here is that there's an annual peak, then an annual rapid increase, rapid drop off, but then it doesn't go to 0. The flu never disappears. And these are all cases recorded in the National Health Service. So these are cases that were serious enough for someone to want to go to a doctor or a community health clinic or perhaps a hospital to be seen. And the conclusion was they'd been diagnosed with influenza. So there's an off season where very little happens compared to the rest of the time. And then the buildup again. If you plot these in the now familiar fashion of just continuing to count until the end of time, you can see, well, you'll see the locations. You have to do the fitting to check that these are Gumford's function growth periods. But the red is Gumford's function growth, and the blue is the rest. We'll see that there's some interesting structure inside the blue as well. But that's what it looked like year after year. And you may be aware of this work by Edgar Hope Simpson. I have a reference to the paper at the end of the slides. It's also in our paper. But in 1983, Hope Simpson, who as a schoolboy had lived through the Spanish flu in England and actually helped nurse some of the teachers to health at his private school, made a lifelong study of influenza cycle. And he has an endearingly low-tech plot in which he produced for the World Health Organization. And in his own paper and the subsequent book, it's apparently photocopied slightly askew, but it has divided up into the north temperate and north tropical zones of the world, and then south temperate and south tropical, seasonal indications of the growth and waning of influenza. And then, of course, for those of you who remember Roll's theorem, it's not a surprise that all hell breaks loose when you cross the equator. So the equatorial season is not a season at all. It's just, it's chaotic. So here's what happens if we zoom in. I hope you can see this in enough detail. There's a linear exit from the initial wave, and then piecewise linear with decreasing growth. Another Gumford's outbreak in the early autumn, followed by linear growth, followed by the next season's Gumford's growth. And what you can just barely see here, maybe, is that the slope here is lower than the slope here. So something happened in the middle, and that middle was, in fact, Gumford's function growth. Here's a little more detail, and you can now, I think this is clear. You can see they're piecewise linear. There are 2 decreasing slope episodes. Then things get kicked off again briefly, and we get another linear piece before the main event. And I suspect that this may well be something like the off-Broadway run of a show or run in the provinces before going to the West End. Maybe those autumn ones are the virus tuning up its variant for the year. Serology ought to be able to tell us the answer to that question. But this is repeated every single year in that Portuguese data set. Something we only discovered in July, I think. So here's if you're really interested, you can find the data from the link that's in the paper. The paper also has these periods, but these are the periods of alternating Gumford's function and linear growth. And we even managed a period of Gumford's function growth in the season starting very late at the end of 2020. It actually started on the 1st of January 2021 that ran through March. So we expect that the same cycle holds everywhere in the northern temperate zone. We haven't been able to verify that yet because we're still looking for data. But COVID-19 actually provides some indirect evidence for this conjecture. So that leads us to what we've called the extended Gumford's function model. We have this alternating cycle: Gumford's growth, linear growth, Gumford's growth, linear growth, again and again and again. And we've shown that that's the case in Sweden, London, Ile-de-France, Ontario, Portugal, in the northern temperate zone, and the state of Rio de Janeiro. We picked that group because we had ordered in descending latitude, and also because they're roughly the same number of people in the at least order of magnitude, 10 to 15 million people in these examples. And then we have one example, which was very much in the news, the state of Amazonas, of the equatorial version, where it's very hard to say what the season is, but except that in Amazonas, their name for this time of the year is winter, even though even though we're in the southern hemisphere, that's the rainy season. That's the season they call winter, and that's very often a series. There are floods, yeah. It's very often a period where there's a peak in all-cause mortality. When you look at all-cause mortality for Brazil as a whole, it's basically shifted by 6 months from any country in the northern hemisphere. But in Amazonas, we have that data daily, where it's just noise, and then weekly, monthly, you see that it does not follow that pattern at all. Sometimes it's on, sometimes it's off. So this occurs equally. We found the same thing in hospitalizations, cases, hospitalizations, ICU admissions, and deaths. We focused on hospitalizations because that's so fundamental to the issue of dealing with an epidemic. The fear that hospitals will be overwhelmed has been absolutely worldwide. However, the cases, ICU admissions, and deaths, we've also seen the same thing wherever we can get the data. If anyone has ICU admission data for Ontario, especially on a daily basis, I would love to have it. I wasn't able to find that. Cases, of course, are problematic, not just because of the lack of diagnoses and the ambiguity in testing, and the difference between different testing regimes in different jurisdictions, but also because the data keeps getting modified after the fact. So it's depressingly easy to find time series with negative cases on given days as people make adjustments. You can find negative deaths as well. Hospitalizations, on the other hand, tend almost universally to be much better data and much less. In fact, I can tell me what the case is in Ontario. I see that there are two different versions of hospitalizations by event date and by date recorded. In Sweden, Brazil, the UK, Portugal, there's a couple of days lag between the release of the data and the events. But those numbers are not retrospectively adjusted. And the importance of that is that that's the only way we can know what we would have seen at the time, what our predictions would have been able to produce in real time if the model had been applied. With cases, you will never know because, I mean, actually, yes.
Are you switching your slides or it's supposed to be frozen here? So I just want to make sure.
Sorry,
so
say that again.
I am not so sure you are flipping your slides or you're frozen in this page.
I've stayed on this page for a while.
Okay, thank you. I'm sorry.
Right.
Yeah.
No, it's okay. It's time to move on.
Yeah.
This was a comment that I decided I should leave in case I had time. So here's what happened. And again, we've done this not because the paper was becoming inordinately long. We haven't shown these sequences for every one of the things that we've shown the Gumford's behavior for. But these are the linear and Gumford's growth periods that we observed in hospitalizations for Sweden, London, Ile-de-France, Ontario, ICU admissions for a bit of a change in Portugal, hospitalizations again in the state of Rio, and deaths in the state of Amazonas. And one of the important features of this, we'll see later, both Ile-de-France and Ontario had these late season waves last spring, March to June. Those are outside of the Hope-Simpson window. So what we've seen everywhere, and this is our indirect evidence for the existence of the same pattern we saw in Portugal and the other northern temperate regions. What we've seen is that COVID-19 outbreaks populated all of those things, even the little one, September, October ones, subsequent to the first wave. But now, and it may be coincidental, post-massive vaccination, we've seen out-of-season COVID waves. These two large ones last spring in Ontario and Ile-de-France, and a much smaller one in London, which nevertheless scared the government into maintaining restrictions last June and July. So our conjecture, and it's continued to be borne out, unfortunately, our conjecture is that we will continue to see perhaps hopefully milder versions, but we will continue to see for some time seasonal outbreaks of COVID-19 in some flavor or other. So just to recap, we've seen this cycle of alternating Gumford's function growth, linear growth, and cumulative events. Now we know how to predict the Gumford's function growth phases. You just fit Gumford's functions and run them forward in time. The predictions are rougher than we'd like. The 10% is not achievable from day one, or even from week 1 or week 2, but they rapidly converge. And then, of course, during these linear phases, well, linear extrapolation is something that even a public health official could do, I would guess. So the forecasting problem is now reduced. This is a great mathematical device. We've reduced the problem to two simpler ones, perhaps. But I'm joking, really, this is an enormous reduction in the problem. Detecting the transition between phases, most importantly from linear to Gumford's function, you can afford to be out a bit when the Gumford's function turns linear, but you don't want to miss the onset of a new outbreak if there is one. And then providing realistic bounds on growth when the Gumford's function doesn't do the job for you before in the Gumford's function phase, before the predictive power really comes online. Or there may be ways to improve reduce the time required to get that convergence. We've started by doing bounds because we know how to do that. We know it works, and we'll work on the other part later. So here's an example in real time of this extended Gumford's function model. After the summer, there was the usual slight increase in activity in September, October. And as you'd expect in the Hope-Simpson picture, certainly when we saw in Portugal, linear growth in November. And then with the data up to December 5th, we detected a departure from that linear growth. The English data hospitalization data has a 2-day lag. So we knew this on the 7th of December. And here's the approach we took. We took the 3 weeks prior to that trigger date. And we used a form of extreme value theory analysis to get bounds for growth of hospital admissions in the initial phase of the outbreak. In case there are any statisticians in the audience, I'll just very briefly say how we did that. Extreme value theory allows you to model the unobserved tail of a sample distribution. So we're applying this, in this case, to the sample of daily admissions. We need a sample that's pretty tightly tied in time to the period we're at. Because in fact, the growth in November of 2021 was only half, less than about 40% of what it was in the same period in 2020. So using that information would have been, well, would have caused massive overestimates of the sort that the SAGE modeling group managed to produce. We found that 3 weeks is fine. We found that in a nice non-data snooping way. That was the first thing we tried, and it worked in the example we tried on, so we just stuck with it since then. So there's no overfitting possible here. And what we do, given that sample, is ask with this extreme value approach, what's the largest, we've got a sample maximum, and what's the average conditional on breaching that? Then do it again and again. What's the average conditional on breaching level 1? What's the average conditional on breaching level 2? And what we do then is take the only thing there's defensible, which is linear growth. We know it will be faster than linear, but we have no reason to choose any form. We have no idea what the Gumford's function parameters will be. So we pick linear growth, and we just look at linear growth at this highest level 3 and linear growth at the lowest level 1. And our prediction is that will contain the admissions. And here's how well it worked in this particular case, which has been running live. So between the 6th of December and the 31st, we said there wouldn't be, there should be no more than 30,613 admissions. And the actual total was about 4% less. And here's the picture. There's the data is in black dots. The level 2 doesn't really mean anything, but we need it to get to level 3. So there are the 3 levels. And what you can see is that the hospitalizations never got outside of that bound until well into the beginning of January. And in fact, since the 29th of December, the prediction errors of the Gumford's function have been under 10% for at least 2 weeks. So the highly predictive phase has arrived, and it arrived before the bound was breached. And in fact, the difference between even these points and the upper bound is very small. So I said in the abstract that I would talk about the inevitability of seeing a Gumford's function. If we start with any phenomenological model that has the form a multiple of a function of t as our model for the cases, deaths, whatever, then that function g is simply the fractional number of cases. So it's a probability distribution. It's a non-decreasing function with values in 0, 1. So it has no choice. It may be a parameterized multi-parameter family of probability distributions, as you see in the Richards function. Generalized logistic distribution shows up there, but it is a probability distribution. And this is where the geometry comes in. Haley Carton taught us that transformation groups produce geometry, and geometry produces invariance, like curvature. And in fact, that's literally what happens here. It's not just an analogy. There's a differential invariant generated by the action of the affine group on the line, the group that the statisticians call location scale transformations. That's what puts the two parameters you always see in probability distributions into them. And the Gumbel distribution is an exceptional distribution under this group action.
Which is natural for probabilities.
Yes, the group action is natural for probability, and has reminded me of I'll come back to that if it's time. So this is something we proved the first part of it 2010 on the beach in Hawaii when I was giving the math department's distinguished lecture series there. We wanted something new for the last talk, which was the really specialist one. So we sat down after breakfast and proved this theorem. And that is that the extreme value distributions are distinguished because they're the only ones that have constant invariance. The curvatures are constant. And the Gumbel distribution is the zero curvature case. The other two, if you're familiar with this, the Weibel distributions are the short-tailed case, the ones that have domains that are bounded above. And then the Frechet distributions are the constant positive curvature, correspond to the fat-tailed case. And these cases are all attractors. If you start sampling the extremes, imagine sampling from out in the tail of a distribution. Of course, the samples are not distributed like the distribution in general, because you're way out in the tail. But there are special cases where the distribution looks the same in the tail as it does everywhere else from that point of view. And those are the extreme value attractors. And the Gumbel distribution is the attractor for the thin-tailed distributions. Those are the ones that you're most likely familiar with. The domains are unbounded above, but they have finite moments of all orders, like the normal, the Laplace, the logistic distribution, so even the log normal distribution. So we proved a version of the extreme value theorem for not the version the analysts like. They don't like things to be smooth. We produce a C2 version that says that distributions in the domain of attraction of an EVG attractor, if and only if the limiting value, its curvature, is the right constant. And that's actually a simplification, a clarification that took goes of things that were left open for more than 70 years. And so our prejudice is for geometry, which a geometer always thinks that they go in and clean things up. But the fact is, these are very beautiful example of differential invariance and the exceptional cases of constant curvature. So what we showed was that there's a very good way to measure the rate of convergence, and that's by looking at these invariants at specific quantiles, as that gives you a numerical invariant. And for many thin-tail distributions, after about the 50th percentile, the difference between a distribution and a Gompertz function fit to that distribution would be invisible at the granularity of the fits you're seeing in this epidemic data. So we have two things that make the push for the Gompertz function. One is that the fits to the data say that the asymmetry is very real. And the derivative peak must be very close to that 1/e level, like the Gumbel distribution. And extreme value theory tells us that if you get above the 50th percentile, you're going to see something that's indistinguishable from Gumbel. And so indistinguishable from Gompertz when you move to the full model. So there's not much wiggle room. If you're not going to be the Gompertz function, you've got to do it between about 37% and 50% of the population being affected. So to recap, this model is a method for navigating these waves. This is something we need. It makes accurate estimates for a short to medium term. And this is absolutely fundamental to dealing with an epidemic. That's our
coincides with the
point of view.
symmetry and all this stuff.
Yes, and there's geometry is symmetry as well. Now, I should say one more thing, since today is Lagrange's birthday. And in fact, the geometry also shows you that not just the Gumbel distribution of the other extreme value distributions, but every smooth probability distribution, C2 probability distribution, is actually a Lagrangian mechanical system in an absolutely natural way. Of course, most of them are extremely boring. Some of them are quite interesting. And that's a topic for another day. But there's also some, there are natural, one of the things that's odd when you, as a geometer, when you look at the epidemiological literature, is that people regard a one parameter, something like the Gompertz function depends on two parameters, two plus the n. They tend to regard that as the solution of a one parameter family of first order equations rather than the solution of a second order differential equation, which is what it actually is. And those second order equations are all Lagrangian dynamical systems, and their dynamics has to converge to the dynamics of these attractors. I think there's probably going to be some interesting mathematics there as well. So one acknowledgement and a note on the fits. The fits here were using a Python routine kindly provided by my brother, Brad Shadwick, from the physics department at the University of Nebraska-Lincoln. You can get the same results, not as elegantly or nearly as quickly using Maple, for example, nonlinear fit package. The point is these are easily accessible through public domain software. Nonlinear regression is not something that requires massive work, and these calculations can be done in nanoseconds. So that's a good place to stop.
Thank you very much, Anna and Bill. So it's time for questions, comments. So you can just unmute yourself and raise a question directly if you don't like using the other ways of registering your questions and you decide to raise the questions. But I would like to start with two questions to you. The first one, and then Bill and Phil, your answer will deserve a Phil's Institute medal, if not Phil's medal. Any consideration on how using this to project the total hospitalizations in this new Omicron wave?
Well, that was Omicron in the English example.
Right.
I have not yet looked at the, I did look earlier on before anything was really happening in hospitalizations in Ontario, for example. But the same bounds work very well, even on cases. The same approach to bounds, even on these explosive case developments. But again, since nobody really knows what a case is, we've preferred to, hospital beds are a scarce resource. And almost everywhere, some medical diagnosis, rather than just a test of unknown specificity, a medical diagnosis is necessary to get you into a hospital bed as a COVID-19 patient. So we regard that as much more reliable. But as I said, it's very important for us to have an accurate picture of what we would have seen at the time when we go back. So we actually, with hospitalizations, we know very well what we would have been seeing in March of 2020. Whereas with cases, that's very difficult, and with deaths, it's very difficult. What you can see in retrospect is once the data noise has cleared out, you get extraordinarily good fits to Gumford's functions for cases, deaths, ICU, and so on. So, but the issue, the hospitalization is two things. One, it's absolutely critical to any response to the epidemic, and two, the data, it's knowable what we would have seen in the past. And then we've been, every day at 1 o'clock here, I look at the latest release from that's 4 o'clock in London, where they're supposed to have the new hospitalization data out, and often they do. But it's always out, within a couple of hours at worst. It's lagged 2 days, then you're done. It's a bit frustrating because the first 2 days of your out of sample prediction are still in the past. Right? So you have to go 3 days ahead before you start predicting the future. I mean, it's still out of sample and you still didn't know what it was going to do. But for it to be useful, you need 3 days of forward accuracy. But anyway, that's.
Thank you.
Data is a big problem.
Yeah, data is, it took a very long time for us to get through some of this because it was extremely hard to find historic data. COVID-19 is the first case where there's been massive amounts of data. So people will be able to wade through these data sets for years and probably find useful things in them. But we found it's a great shame that the epidemiological modeling community hasn't put together a database with historic examples. I didn't get to it, but David Earn gave us some of his Spanish flu data from England, and we found these waves of Spanish flu were interrupted by linear growth, which is an argument for different virus, a different variant. This is something, actually David's paper on this argued that there wasn't a new variant, it was just changed behavior. This is indirect evidence for a variant change between the waves. Anyway, this is something that serological studies should be able to determine whether these, I mean, for example, that there was a change in England. There was a change through different variants as we went through the first few periods. So that's completely consistent with this idea that it became endemic just the way flu does. Then we got a new variant in the new season and so on. And I'm sure that serology has been done, and eventually the data will become available.
Thank you, and Bill. Other questions before I'm throwing all my questions from the audience? So maybe I can ask the next question. So I have tons of questions actually. The compass function, I believe, had 3 intrinsic parameters, and this might be a coincidence that a simple epidemiology model have 3 major parameters as well. And this is just it might be just coincidence, but if epidemiological process like COVID is highly regulated by other behaviors and interventions, so the epidemiological process will probably involve more parameters. And I'm just wondering how really, especially nowadays with all those rapid behavior change, decision, policy switch, how group-based model is compared with traditional
Right.
outbreaks, and I just don't know. It's only I just find it
so
interesting.
that's a
Has 3 parameters. Yeah.
Absolutely, that's a very interesting question. I don't know if you know about Gabriela Gomez's work on this. But she's been convinced that the key was the heterogeneity of the population, and she's modeled the heterogeneity in England and Scotland already, and produced with an SEIR model, a very good approximations to the actual data. Now we've been talking with her about that, and of course the thing is, now that she's got a good approximation to the actual data, it pretty much has to be Gumford's function linear, right? And it is. The question is, how can you use the need for, can you use the fact that it ought to look like a Gumford's function and linear alternation to tune the heterogeneity, to actually discover what the right model would be, and I think that's quite likely the case. There was also a group at Max Planck in Munich, I think. The reference is in our paper, but I've fortunately forgotten the author's name. And what they showed this, that using heterogeneity with a particular power law probability function, they also reproduce very well German data. Well, that means they reproduce very well Gumford's behavior. So there's some intriguing links there, and I think that's. I mean, we're hoping that we're hoping with Gabriela to go through that influenza observatory. I think this is a real goldmine of data, and nobody was doing anything there, right? It's simply what happened through the seasonal changes. So it's a good base case, if you like, for testing more complicated models. And there we quote in the paper the head of the English modeling group, Graham Medley. Is his web page, his home page, he has an extended thought about how heterogeneity cannot possibly be right, but you're stuck with it. How do you vary away from it, and so on? And we think that perhaps the answer is in a way that pushes you towards the Gumford's function behavior, because that empirically is simply there.
Yeah, just clarify heterogeneity of transmission.
Well, this is actually there were. Gabriela has heterogeneity of transmission, and also a heterogeneity of susceptibility. In both cases, you get the same effect, but in very different degrees. And in fact, it's the transmission heterogeneity that most closely fits the Gumford's picture so far.
Thank you. Now I understand why you keep talking about Portuguese data, given your connection to Gabriela. Did she? I hope she would ask you questions about how those parameters are related to the epidemiological parameters. That could be a very we really have only started to think about that. Right. It must, logically, this ought to be there. But right. The fact is, once you introduce a reasonable heterogeneity, you get something that looks very, very much like the actual data. Well, that's a convincing start, right? And but it took her a very long time to go through that, and you know the story, but she had a great deal of difficulty with referees. That's on at the beginning for the most outrageous reasons, not scientific reasons, but political reasons. But anyway, that seems now to be in the past, and the papers are on their way to being published. May have been published by now, I'm not sure. Thank you. The last question, that time's running out, so I'll leave the last question for Martin. Martin, raise your hand.
Very kind of from one heterogeneity to another in terms of how much you had an algorithm for switching between the Gumfords to the with extreme value theory, which I'm not too familiar with, to going over from linear to the Gumpert's solution, sort of Gumpert's fit. How sort of amenable or alterable is that to other data, say people picking up new strains from genomic surveillance, that kind of thing? Is there ways of that it could be extended to have inputs from other data sources such as that, or even
no? I think the answer is yes. But what we're doing is something very simple to begin with. We're just looking at the daily data as it comes through. We're not trying to see anything else. But that's all that goes into it. So the source is it's independent of the source, if you like. So that would be interesting to look at. We're hoping we'll see some more information through the Omicron phase. How is that going now in Ontario? Are the hospitalizations increasing? They must be at some point.
Well, this is recorded, so it's a politically sensitive question. I think the cases, the hospitalization and ICU beds are still going up, but it's I think it's starting to kind of stabilized. No. I think that's
the last time I looked, which is a couple of weeks ago now. The hospitalizations were still in a linear growth mode, so I just stopped at that point. But I should look again. Let's hope they stay in the linear growth mode. That would be nice.
Yeah, what I see in comparison with what different growth rate, and it's in the
yeah. This, I mean, of course, you can, if you know the serial interval, then you can calculate the RT directly from the Gumford's fit. But I don't know what if people really have a firm grasp of the serial interval. So we haven't tried to do that. And the measurements of R tend to be very, very noisy. Right? You see, at least the ones that are published in England have error bars that are more or less the size of the graph, the size of the page. So, but again, in retrospect, now once the case numbers are realistic, you can go back and see how well the R values agree with what was measured. But I think there's a lot of potential interaction between this and the traditional approaches in many different aspects.
Great. So before you start asking me questions, Bill and Anna, so I want to thank you again for your time and for a very interesting talk. And again, we're looking forward to you back to the Fields Institute for sometimes physically, so to listen to you.
That would be nice for everyone, wouldn't it? Thank you. Yes. Well, I may see you at the conference over the next couple of days. I'm not sure if the time is going to line up correctly, but we'll see.
It's going to be a very exciting event. Thank you again. Yeah, thank you for help us to promote this event. So again, to echo what Bill just said, the institute, the network having 2 days events tomorrow and Thursday afternoon, and have a look. And if you have not registered, please do register, because that will save you time to get into the very beginning of the event.
Well, that's great. Well, thanks for the invitation. Good to see you again. Yeah. Nice to meet you, Sarah.
Yes, thank you so much. That was fantastic. And I've just put the information and registration link into the chat if anyone's missed it.
Oh, great. That's good. I've got an email today with it. So
right. Thank you so much. That was excellent.
All right. Thank you. I enjoyed it.